to give the first talk of this conference, Professor Graham Priest from the City University of New York, the Graduate Center. I want to tell you that Professor Priest is considered one of the most important philosophers recently. He has published many books, especially on topics concerning philosophical logic and its metaphysical and ontological implications. So Professor Priest published books like Towards Non-Being, One, Doubt Truth to be a Liar, an introduction to non-classical logic, a very short introduction, many interesting and important books for contemporary research on logic. So he gave already 2 talks in our local seminar, Logic in the Airplane, and it's a very important occasion for all us here to have his presentation today on Gödel's theorem and paraconsistency. So, Professor, please be welcome again here at the University of Brasilia, and I invite you to come to the table. All right.
Okay, so I have to use this, right? So I feel like an old rock star. How do we do the translation? We don't. That makes things easy. Okay. If I walk around, is that okay? Can you? Oh, okay. Can I move while I talk? Yeah. Okay. Well, look, first of all, let me thank the organizers very much for putting on this event, which is terrific. This is a great auditorium. I've never been in anything like it, so this is fantastic. So thank you to all the people who've made this possible, and that means the people who've coughed up the money as well as organized. So I want to talk about Gödel's theorem. This is the first incompleteness theorem. I'm afraid I'm not familiar with Professors Granger and Viemin, so I can't comment on how this relates to their work. I'm happy to leave that to others to do. Because Gödel's theorem is certainly very important about how we reason, in particular how we reason in mathematics. And Gödel published his theorem in 1931, and I think undoubtedly it's one of the most profound results in mathematics in the 20th century. Unfortunately, no one can agree on exactly what the importance is philosophically, and so I want to talk about part of that debate. Paraconsistent logic, that is logics in which you can have contradictions without explosion, so contradictions are kind of limited, they don't go everywhere. Paraconsistent logic puts a whole new light on Gödel's theorem, which I guess most people are not familiar with. So what I want to do in this talk is talk about the relevance of paraconsistent logic for Gödel's theorem. So the talk is quite technical, but let me take it slowly and let's see what we can do. Okay, so that was the introduction. You've had that. I want to talk about inconsistent arithmetic and its relevance to Gödel's theorem. But to do that, I'll have to tell you a little bit about Gödel's theorem and about paraconsistent logic, because not everybody knows this material. So a lot of the time, I'm going to talk about this, and then we'll get on to inconsistent arithmetic. Okay, so first of all, Gödel's theorem. If you open a textbook on mathematical logic, you will often find a statement of Gödel's theorem as something like this. Any axiomatic theory of arithmetic with appropriate expressive capabilities is incomplete. Okay, that's not a good statement. This is the correct statement. The theory must be either incomplete or inconsistent. Now, if you're working in classical logic, if the theory is inconsistent, it's trivial. You can prove everything. So people can justifiably ignore the inconsistent option. But once you move to a paraconsistent logic, this is no longer the case. To assume is that there's a formula with two free variables, bx, y, which defines the proof relation in T. That is, if n is the code of a proof of A in T, then B, n, angle brackets A, is true in the standard model. And if n is not the code of a proof of A in T, then its negation is true in the standard model. Third assumption, you can define prov y as there is an x such that x is a proof of y, then prov is a proof predicate for T. That is, if you can prove A, then in T you can prove that prov A. And the fourth thing you need is that there is a formula G of the form not prov G. There are some subtleties here, but I'll slide over them. Okay? So with those four assumptions, you can prove Gödel's theorem. So this is how you do it. Okay. Suppose you can prove G. Well, then you can prove not prov G, because that is G. But if you can prove G, then you can prove prov G, because prov is a proof predicate. So what we see then is that if you can prove G, T is inconsistent. Okay, now suppose that T is consistent. Then you can't prove G, we've just seen that. So no number is the code of a proof of G. So for any n, the negation of B n G is true in the standard model. Okay, so therefore the universal quantification of that is true in the standard model. And we do a bit of logic chopping here. So that's equivalent to this. So we need a few quantified principles. But that is just the negation of prov G, and that's G. So supposing that T is consistent, G is true in the standard model. You can't prove G, but G is true in the standard model, so the theory is incomplete. All right? So if the theory is inconsistent, it's incomplete, but by contraposition, if it's complete, it's inconsistent. So this is a proof of Gödel's theorem, which works, and we've made very little assumption about the logic, a few assumptions about how quantifiers behave. That's all. Okay, so as I said, most people who talk about Gödel's theorem assume you must be operating in a consistent context, but I want to examine the inconsistent possibility. So what we're going to be doing is looking at inconsistent arithmetics and what happens to the Gödel sentence in those arithmetics. Now, to do that, you need to understand a little bit about paraconsistent logic and some of its meta-theory. So I'm going to give you the background that you need to understand this. Okay, so a guide to paraconsistent logic. There are, of course, many paraconsistent logics, and this country is justifiably famous for its work in paraconsistent logic. I'm going to describe one system of paraconsistent logic, a system called LP, which is simple and robust and will do what we want it to do today. Okay, so the language that we're going to use is a standard first-order language. Nothing new there. An interpretation is going to be a structure D, which is the domain of quantification, and delta, which is the denotation function. So that tells you the denotations of the constants, the function symbols, and the predicates. So D is an empty domain of quantification. The denotation of any constant is a member of D. If Fn is an n-place function symbol, then its denotation is a function from n tuples in the domain to D. So this is all standard classical logic. This is where it's different, because in classical logic, well, come back to that, the denotation of a predicate is a pair. The predicate is going to have an extension and an anti-extension. So the extension are the things of which the predicate is true. The anti-extension is the things of which the predicate is false. And you have to treat them even-handedly. So in interpretation of a predicate is a pair, the extension and the anti-extension. I'll write them like this with a plus and a minus, such that the extension and the anti-extension exhaust all the interpals of the domain. Okay? So in this logic, there are no truth value gaps. You can't have something that's neither true nor false. This essentially rules this out. But you can have things which are both true and false because the extension and the anti-extension of a predicate can overlap. And the identity predicate is just, it's what you'd expect. It's as you get in classical logic. Okay, so given interpretation, the next thing we need to do is specify the truth and the falsity conditions. Of course, in classical logic, once you know the truth conditions, then the falsity conditions follow, because they're just, falsity is the complement of truth. But in a paraconsistent logic, truth and falsity are independent, so you have to give truth conditions and falsity conditions. So, first of all, we finish off denotation. So if you've got a term, function symbol and end terms, what's its denotation? Well, it's exactly the same as classical logic. You apply the denotation of the function symbol to the denotations of the terms. Everything standard there. The truth, that's the little plus here, of an atomic sentence, well, this sentence is true just if the interpol of the denotations of the terms are in the extension of the predicate. And for falsity, that's the little minus, this formula is false if the interpol of the denotations of the terms is in the anti-extension of the predicate. And the extension and the anti-extension can overlap. So something can be both true and false. Okay, the rest is what you'd more or less expect. So a negation is true if the thing negated is false, and it's false if the thing negated is true. A conjunction is true if both conjuncts are true, and false if one or other conjunct is false. A disjunction is true if one or other disjunct is true, and false if both disjuncts are false. And note that the material conditional is defined in the same way as usual. So you don't need to give separate truth and falsity conditions because you define material implication as this thing. Okay, quantifiers, there are many ways to do the semantics of quantifiers. You can use satisfaction, but I've always thought that the easiest way to do semantics of quantifiers is just to help yourself to enough names to ensure that everything in the domain has a name. So what we're going to do is extend the language to a name for every object in the domain. So if D is in the domain, let's add this new constant, KD, which refers to D. So we know now that every object in the extended language has a name, and that allows us to give truth and falsity conditions for quantifiers in the easy way. So a universally quantified sentence is true if every object in the domain satisfies it, that's what that says, and false if some object in the domain makes it false. And then for the particular quantifier, you just do the dual thing. Okay, and now let's have a definition of consequence. So if A is a model of the formula A, just if the structure makes A true. Same as in classical logic. A is a model of a set of formulas, sigma, just if it makes every formula in sigma true. If it's a model of every formula. And the definition of consequence, if you've got a set of formulas set of formulas sigma, then A is a consequence of that, just if every model of sigma is a model of A. So this is standard stuff from the model theory of classical logic. Okay, so that is a specification of the paraconsistent logic LP. Now, some facts about it. First of all, if the extension and the anti-extension of a predicate are disjoint, then this is exactly classical logic. Because the only way that these truth conditions and falsity conditions actually differ from classical logic is that they've come apart. And if the extension and the anti-extension don't overlap, then this is exactly classical logic. Okay? So classical interpretations, classical models are special cases of LP interpretations. So every classical model is an LP model, but there are more LP models. So what that means is that if something follows in LP, it follows in classical logic. But yeah. Well, classical logic is negation complete in the following sense. Every formula is either true or false or not both. So we're not talking about theories, we're just talking about interpretations at the moment. Okay? And in classical logic, every sentence is either true or false or not both. And if you insist that the extension and anti-extension of every predicate don't intersect, that's exactly what you'll get. Okay? Yeah. Look, thank you for the question. Please feel free to ask questions of clarification, because I know that this stuff is probably unfamiliar to many of you. So if you want me to explain some more, please ask. Okay. So any logical consequence in LP is a classical logical consequence, but the converse does not follow, because this inference from A and not A to B is valid in classical logic. But it's not valid in this logic because A can be both true and false, where B is just plain false. So this means that the logic is a paraconsistent logic. Okay. So the fact that an inference is valid in classical logic does not imply that it's valid in LP, but there's something kind of interesting, namely, if you have no premises, so there's a special case in which sigma is empty, then the two logics coincide. So LP and classical logic have exactly the same logical truths. What they do not have is the same consequence relation. This is a reason why you cannot identify a logic with its set of logical truths. Here are two logics with the same set of logical truths, but with a different consequence relation. Okay. Now, so that's the background in paraconsistent logic. And there's one more thing that you need to know before we can get to arithmetic, and that is a little bit about the model theory of paraconsistent logic, this paraconsistent logic. So I need to explain to you something about collapsed interpretations. So let A be an LP interpretation. And that includes classical interpretations as well, because as I've told you, every classical interpretation is an LP interpretation. What we're going to do, essentially, is collapse that interpretation. Let me show you how. So tilde is an equivalence relation on the domain of A. So an equivalence relation is something if this is a domain, an equivalence relation is something which chunks the domain into disjoint equivalence classes. Okay, that's what an equivalence relation does. So tilde is an equivalence relation. And moreover, it's a congruence relation on the denotations of the function symbols. Now, what that means is essentially this. If you take two things in the same chunk, okay, and you apply the denotation of one of the function symbols to them, you're going to get things which are in the same chunk, okay? So applying the function to two things in the same chunk is always going to take you to the same chunk. So mathematicians call this a congruence relation. And you need the equivalence relation to be a congruence relation. Okay. Now, notation if D is in the domain, I'm going to write the equivalence class of D as D in square brackets. So if D is in the domain, D in square brackets is the whole chunk. Okay, so now I'm going to define the collapsed interpretation. So it has a domain and a denotation function, and the domain is just going to comprise the equivalence classes, the chunks. The denotation of every constant is going to be the chunk which the denotation of C was already in. The denotation of the function symbol is just going to be, well, you take some members of the chunks and you apply the function to that, and the chunk that's in, that's when you need it to be a congruence relation. And, okay, these are the interesting bits. Let me, you can read this for yourself. Let me just draw you a picture of what's going on. What we're going to do essentially is we're going to identify all the things in one chunk. So this chunk here is going to satisfy predicate if something or some things in this chunk satisfy it. Okay? So what we're really doing is identifying the things in a chunk. So suppose, for example, that Alex is in the chunk and I'm in the chunk. Okay? We're going to identify him and me to produce the chunk which contains both of us. So the chunk is Brazilian, because Alex is Brazilian, and it's Australian, because I'm Australian. It's not Australian, because Alex is not Australian, and it's not Brazilian, because I'm not Brazilian. So what we're doing is identifying all the things in a chunk, and the chunk is going to have all the properties of any individual member. So we're sort of collapsing together distinct things to produce a very inconsistent object. Okay. That's essentially what this says. Okay, now, this is the important fact about collapse. Suppose you've got any LP interpretation and you collapse it in the way that I've told you. Then, okay, skip over that. This is the important thing. If A is true before you collapse, it remains true after you collapse. And if it's false before you collapse, it's false after you collapse. So you never lose truth values when you collapse. You can get new stuff, new things can become true or false, but you can't lose old stuff. And this is important because it means that if you start with a model of some theory, when you collapse, you get a model of that theory. You might get a model of more, but everything true before you collapse is true after you collapse. Okay, so that's the kind of background you need to know to follow what I'm going to say about arithmetic. Let me pause for a second, because we've been through quite a lot of technical material. Would anyone like me to explain any of this further? Okay. So that's the background. Now I want to talk about arithmetic. And what I'm going to show you is that, first of all, that there are inconsistent complete arithmetics. And then we're going to talk about what happens to the Gödel sentence in those arithmetics. And then in the last few minutes, I'll just gesture at some of the philosophical implications of this. So let L be the usual first-order language of arithmetic, just as you find in any textbook. Let N, boldface N, be the set of sentences true in the Standard Model. So this is what logicians call the theory of the Standard Model. It's just the set of sentences true in the Standard Model. And let fractor M be any model of N. So it's any model that it makes N, all the sentences in N true. And we know there are lots of those classically. You know, there's one standard model, but we know there are lots of non-standard classical models. Okay? We're going to produce now some non-standard paraconsistent models. So if you take M and you collapse it, and to get M tilde, then what you get when you collapse is a model of n. And that's just a result of the collapsing lemma. Okay? I didn't prove the collapsing lemma for you. You can take my word for it. It's not difficult to prove, but for today's purposes, just take my word for it. So if you take a model of all the things true in the standard model of arithmetic, you get a model of the standard model of arithmetic. Okay, so let's collapse some models and see what happens. Suppose that M is any non-standard model of arithmetic. So some of you will know about this stuff. In classical logic, there are many non-standard models of arithmetic, and they sort of look like this. Okay, they have all the natural numbers, and then after those, there's some junk, some non-standard numbers. Okay, these are perfectly natural classical models. What we're going to do, essentially, is collapse all these guys and make one of them. Okay, so how do we do that? Well, we're going to define an equivalence relation, which is also a congruence relation. So D tilde E, just if D and E are standard and D equals E. So we're going to leave the standard numbers alone. We're not going to mess around with those. Or D and E are non-standard. Okay, so D tilde E if both D and E are non-standard. So this is a congruence relation. You can check that if you like. And we're going to collapse with that congruence relation. So what we get is a structure that looks like this. So we've got all the natural numbers. Okay, we've left those alone. And we've collapsed all the non-standard numbers to a single number, which, so this is the graph of the successor relation. So 1 is a successor of 0 and so on. And everything in I has a successor, which is itself I, because we've identified I and its successor for every non-standard natural number. Okay, so our structure looks like this, and it's a model of all the truths in the standard model, so it's complete, but it's inconsistent because something is its own successor, namely this guy I. And of course the negation of that is true in the standard model, so the theory is inconsistent. But it's not trivial because this is not true. We've left 0 and 1 alone. So we haven't done anything to affect what holds as 0 and 1, and in particular, 0 equals 0 prime, 0 equals 1, is not true in this model. So it's not trivial, okay? Really, the inconsistencies all concern this guy here. So that's an example of a collapsed interpretation, which shows you that you can have a complete arithmetic. I mean, in that theory, in the theory of M tilde, everything is either true or false, but some things might be both. Okay, let me give you a second example. Okay, so let M this time be the standard model. All right, this is, the standard model of arithmetic. And I'm going to define a new congruence relation. So N and P are natural numbers greater than 0, and D tilde E, just if D and E are less than N, and D equals E. So for things less than N, we're not going to frig around with them. So we're leaving the things less than N alone. But if D and E are greater than or equal to N, then D tilde E, just if D and E are identical mod P. So in other words, we're doing sort of clock arithmetic. Okay, so in clock arithmetic, if you add 12 to a number, you get the same number, okay? 1 o'clock in the morning, you add 12, you get 1 o'clock in the afternoon, 2 o'clock comes 2 o'clock. So really, anything that differs by 12 is, you get the same, okay? That's clock arithmetic, or what mathematicians call modular arithmetic. So we're going to take all the numbers greater than n and identify them mod p. So p does not mean prime, p means period. Because what does this structure look like? Well, okay, the structure of the collapsed model looks like this. So we haven't done anything with the numbers less than n. We've left those alone. right? But we've made sure that there's a loop after that, it's like a clock, such that once you take any number and you add p to it, you get back to where you started. So there's a cycle, there's an initial tail where things behave classically, and then there's a cycle that follows that. Yeah.
Can I compare the numbers that come after n to the numbers before, like n would be 0, n plus 1 would be 1, and so on?
So anything true in the standard model? Okay. Anything true in the standard model is true in this model. So, for example, in the standard model, 0 is less than everything. So 0 is going to be less than all these guys, right? So everything behaves perfectly normally here, but when you get to here, something odd is going to happen because n is going to be less than itself. Okay? So that, of course, is inconsistent, but it's an inconsistent model. So strange things happen once you get to the cycle, but everything down here is perfectly normal. Okay? So what do we know about this structure? Well, first of all, something is its p times successor. So there are some things such that if you add p to them, you get back to where you started. Okay? However, the model is the model is not trivial because, again, we haven't fiddled around with 0 and 1. So in this model, it is not true that 0 is 1. There are other contradictions, but not concerning 0 and 1. Okay, now, I give you this model because it has a particularly important property. It's finite. The first model I gave you was not finite. This one is, okay? So have a look at it, okay? The domain of the collapsed interpretation is finite. That means that the truths of this model and the faults to this model are decidable. Because if you've got any finite structure, there's a way of deciding whether something is true or false in it. Okay? Undecidability comes from the fact that you're dealing with infinite domains. But if you've got a finite domain, then the universal quantifier is just a big conjunction. The particular quantifier is just a big disjunction, so you can apply truth tables. So the set of things which are true in this collapsed model are decidable, and that means they're axiomatic, because decidable sets are axiomatic. That's a sort of small definition in recursion theory. Now, this particular interpretation is finite and axiomatic. There are infinite interpretations which are also axiomatic, but that's harder to prove. So I gave you this simple example. But what you have now seen is that there are axiomatic theories which are complete. In other words, everything is either true or false in the interpretation, but inconsistent. Some things can be both true and false. So these models are models of inconsistent, complete arithmetics, but they're not trivial, okay? It's not the case that everything holds in these models. All right. So, I started by saying that once you move to a paraconsistent logic, you can have inconsistent but complete arithmetics. And you've now just seen what these are like, or some of them are like. Okay. So the next question you might want to ask is, what happens to the Gödel sentence in these things? So we know that you've got a model of everything true in the standard model. What happens to the Gödel sentence? Remember, in the in the consistent case, it's going to be such that neither it nor its negation is provable. What do you think is going to happen in the inconsistent case? Let's see. Okay. So let T be any axiomatic arithmetic which contains whatever is true in the standard model. And we've now seen there are such things. Okay, let prov x be the arithmetical predicate which defines T in the standard model. So this theory is axiomatic. So in particular, the proof predicate is arithmetic. That means you can define it in the standard model. And suppose what that means is if you can prove A in T, then prov A is true in the standard model, so you can prove it in T. And if you can't prove A in T, then not prov A is true in the standard model because prov defines the proof predicate in the standard model, and so its negation is true, not prov A is true in T. Okay? So this is a fact, this is a consequence of the fact that you're dealing with an axiomatic theory whose proof predicate is representable in standard arithmetic. Okay, so let G be the Gödel sentence. Let's see what happens to it. Well, either you can prove G or you can't. In either case, you can prove not prov G. Because if you can prove G, well, G is not prov G. And if you can't prove G, well, then you can prove not prove G. Okay, that's by this condition. So in either case, then, you can prove not prov G. But of course, that is G. So by the first condition of a proof predicate, you can prove G. So you can prove G, and you can prove its negation. So the Gödel undecidable sentence is both provable and its negation is provable. So in the consistent case, you can prove neither the Gödel sentence nor its negation. In this inconsistent arithmetics, you can prove the Gödel sentence and its negation. All right. So let me spend the last 10 minutes talking about philosophical issues. This is much harder work, okay. But we've done with all the technical details. You'll be happy to know. Okay, so let's think some more about the Gödel sentence, all right? We know that you can prove neither it nor its negation in the incomplete case, and you can prove both it and its negation in the inconsistent case. Now, which of these is actually more plausible? Well, look, behind Gödel's proof, there is a paradox. And it's rather like the liar paradox, except that it involves proof rather than truth. So let G be the sentence G isn't provable. And prov here, I don't mean the provability predicate of some formal system. I mean just, something like it's provably true that in natural language. So take a sentence which says, hey, I'm not provable. All right, so suppose you can prove it. Well, then it's true, because anything you can prove is true. And G is not prov G. So if G isn't provable, it is provable. So by, standard logical move, you've just proved it. That is, you've proved G. That is, you've proved that G is provable, because you've just proved G. Okay, so you have a paradox. G is both provable and not provable. This is the analog of the liar paradox, but it's for provability rather than truth. So, of course, there's an enormous question about how you solve the liar paradox. The literature is enormous. But dialethists, such as myself, hold that the correct way to solve the liar paradox is to just accept that the liar sentence is both true and false. So if the sentence L is false, then that sentence is both true and false. Now, if you accept a dialethic solution to the liar paradox, then the natural thing is to accept a dialethic solution to this paradox. Okay, now we're dealing with provability, not truth, but the two would seem to be very closely related. So if you accept a dialethic solution to this paradox, which is sometimes called Gödel's paradox, if you accept a dialethic solution to Gödel's paradox, what you really want is an inconsistent arithmetic, one such that both G and not G hold. So this is one reason why you might prefer an inconsistent arithmetic, because it gives you the same kind of solution to Gödel's paradox as you get for the liar paradox if you are a dialethist. That's one reason. Second reason. This is sometimes called Loeb's principle, okay? So consider the sentence, if you can prove A, then A. Now, that damn well looks as though it's true. Should be, okay? Because, hey, whatever you can prove is true, so you expect that to be true. But you cannot prove this in consistent arithmetic. So this is Loeb's... Loeb's theorem says if you can prove this, you can already prove A. So you cannot have this for every A in classical arithmetic, even though it's damn well intuitively true. Okay? You can only prove some instances of it, namely the ones for which you've independently got a proof of A. And that seems odd. I mean, no, this thing is true in the standard model, so you can add it to the arithmetic. But if you do that, you're messing around with the axioms. So you've got to, you can add this, provided you're dealing with proof in the old sense. But if you add this as an axiom and you've got proof in the new sense, well, then you're back with the situation. So, I mean, you cannot have this principle in generality in a consistent arithmetic. But you can have it in a paraconsistent arithmetic. So here's why. Okay, so for any A, you can either prove it or you can't. In the first case, you can prove the Loeb principle. That's just because this is material conditional. If you can prove A, you can prove this conditional. And in the second case, by the properties of the provability predicate, if you can't prove A, you can prove not prov A. And so, again, you can prove this because this is a material conditional, and you've just established the negation of the antecedent. So what we've just seen is that Loeb's principle holds in these inconsistent arithmetics. So you cannot have this inconsistent arithmetics, although it seems you ought to have it, because, hey, it seems to be true. But you can have it in inconsistent arithmetics. So these are two reasons why you might prefer an inconsistent arithmetic to a consistent arithmetic. So, last couple of minutes. I've been telling you that arithmetic is inconsistent, right? That's sort of a shocking claim. So presumably you want to object. So you may have many objections. Okay, we can hear those. Let me just give you a few possible objections. An inconsistent arithmetic doesn't prove enough. Okay, this one's a non-starter because everything you can prove classically, everything true in the standard model is true in this arithmetic. So it's not the case that you haven't got enough. That's the worry with the incomplete case. If there's a worry, it's not that you haven't got enough, it's that you got too much. Okay, so second objection, it proves too much. Why might you think it proves too much? Well, you might have a very general reason for this, because you might think that the principle of non-contradiction is true. Okay? No sentence can be both true and false. So if you believe that, then of course you're going to reject dialethism, because dialethism exactly denies this. Now, over the last 30 years, there's been a debate on whether or not how good the principle of non-contradiction is. And one thing that's transpired in the debate is that it's actually kind of hard to defend the principle of non-contradiction without begging the question. So, I mean, if you believe in the principle of non-contradiction, then you've certainly proved too much, because you've got inconsistencies. And where the debate goes now is, well, whether you should accept the principle of non-contradiction. That's a big issue, as I've indicated, and I'm not going to go into that in this lecture. If you want to take it up in the discussion or in the tea room, that's fine by me, okay? But you might have very general objections to inconsistency. That's one thing. But you might have more limited objections. Maybe, you know, inconsistencies can be true sometimes, but hey, you don't want them in arithmetic. Because, and you might think, well, you know, inconsistent arithmetic would ruin the applications of arithmetic. So, you know, arithmetic is not just a pure mathematical theory. We use arithmetic all the time when we count and, you know, add up and do science and so on. And you might think that the fact that you can prove certain inconsistencies is going to ruin arithmetic for its applications. Okay. Now, let's think about this. In all these inconsistent models, everything behaves fine for a while, and then things go inconsistent, you know, in due course for some number. Let's call it n. So up to n, everything is consistent. Then after n, strange, inconsistent things happen. How big is n? Let's suppose that it's fucking enormous, right? So it's bigger than any number. Okay. So it's bigger than the number of atoms. It's bigger than the number of atoms in the cosmos. It's bigger than the number of games of chess you can play if every atom in the cosmos were a chess piece. Okay? It's so bloody enormous. It has no practical significance whatsoever, because it's bigger than anything with a physical meaning. So you know that standard arithmetic is okay until you get to this bloody enormous number which has no physical significance. Okay? So what it means is that if the least inconsistent number is so bloody big, then it's not going to affect applications, because all the applications concern things which have physical significance. Okay? So the inconsistency arithmetic on that assumption is not going to have, I mean, it's going to be an interesting fact about pure mathematics, but it's not going to affect any of the applications of pure mathematics. Okay, so that's the end. Let me just remind you where we've been. I've been talking about Gödel's theorem, and in particular the Gödel sentence. This sentence is not provable. And in consistent logics, consistent arithmetics, neither the Gödel sentence nor its negation is provable, so the theory is incomplete. But what we've now seen is that there are inconsistent arithmetics which are complete but inconsistent. And in particular, then you can prove the Gödel sentence and its negation. Okay? And then just at the end, I raised a few thoughts about what this might mean philosophically. So the technical stuff is not contestable. The technical stuff is just, beyond argument. These are just results of pure model theory. What is, of course, contentious is what this means, and whether one should take an inconsistent arithmetic as the correct arithmetic, not the standard model, okay, which is just a chunk, or gives you a chunk of what's true about numbers, but a proper chunk. So there's all the stuff true in the standard model, and then some more. Okay, now that's contentious, and I've done no more than start a discussion with respect to that. We can take that up in questions or in the tea room or by correspondence, that's fine. But at least now, I hope in this talk, I've opened your eyes to some new possibilities. And, you know, philosophical discussions about the philosophy of mathematics take off from technical results. Well, I've given you some technical results today, which you may not have known about before, and this, I think, opens a whole new page on the discussion of the philosophical significance of Gödel's theorem. And, of course, where that goes, well, time will tell. Thank you.
We have some time for questions.
Well, again, I enjoyed very much the talk, and what I have to say is small and limited. It's just I want to ask you if you know of some works I have met many years ago. Some people, because I was working about non-standard mathematics, as I told you at some lunch, and some people in that school were trying to, they realized that to have a non-standard discourse, what we needed was an infinitely large natural number. It was enough, because if we have an infinitely large natural number, then by taking fractions, we can have infinitely small numbers, and we can do the game of non-standard mathematics on that basis. And so the issue was, how should we introduce an infinitely large number? Classically, Robinson was doing that with using ultra products or something like that. And some people realized that it was tempting to do that only at the level of arithmetic, without the whole machinery of set theory. And some people realized that one way of doing that was using Gödel's incompleteness theorem. There is a paper from Liu, which is from 1980, I think, which does that. He defines a natural number on the basis of Gödel's sentence. With a little trick, we turn Gödel's sentence into a sentence of the form exists x such that a of x, and this sentence happens to be provable, but we know for sure that for any actual natural number, k, a of k is not provable. Yeah. So we have introduced in that way an infinite large natural number.
But it's omega incomplete, right? It's omega incomplete.
It's only...
Oh, it's a question. This system is omega incomplete.
Yes.
Yes.
Yeah, exactly. You're right. So, sorry, I didn't hear your omega. Sorry. Good. But then, the description you gave of your inconsistent arithmetic at the end of your talk, philosophically, with all the problems beginning, inconsistency appearing only at a very, very far distance with this bloody number you made. So it's quite a similar point of view. So this is my first remark. Did you know about that? Do you know more connections between your work and this kind of work?
Okay, can I take your question separately, because otherwise I'll forget.
Okay.
So, look, I'm not familiar with the paper that you mentioned, so I'd be very happy if you'd give me the reference.
Yes.
Okay? Secondly, I am familiar with some work in this area. So there's a beautiful construction by the mathematician Conway called surreal numbers,
yes,
which allows you to have infinite numbers, infinitesimals, and a lot of other things. So that's a beautiful construction. So that I am familiar with. Now, I think in all the systems that we're talking about, they are consistent, okay? And as long as you remain consistent, you're going to get the sort of issues that I've been talking about. So what I've been talking about is what happens when you sort of transgress beyond the consistent. And the constructions that retain consistency are going to have exactly the same kind of features as Peano arithmetic. Of course, they have other interesting properties, but they're the same as Peano arithmetic in the sense that they're consistent. What I've been doing is saying, hey, what happens when you go beyond the consistent?
Okay, so I think it's enough. I have another question, but it would be for private.
Okay, we can talk in the tea room or the bar or whatever.
Greg, I have a technical question. Could you show me the slide about Gödel sentence in the end of?
Yeah, I can if I can find the remote. Okay. Zoom.
No. Prior.
Yeah, this thing.
No. One more.
One more?
Mm-hmm. More. Yeah, that's it. Capital N is the set of Gödel's number in the top. Capital N.
Well,
T, that's it.
No,
capital N
is a set of
N.
sentences true in the standard model.
Okay. How do you know that proof X there exists?
How do I know that the
Yeah.
probability predicate exists?
There is
Okay.
a proof X defining this
Okay.
set. That's the
Well,
point.
So for the
I don't
following,
know.
okay, for the following reason. Oh, sorry. Okay, for the following reason. This theory is axiomatic. Okay, that's important. And because it's axiomatic, it's definable in the standard language of arithmetic. So I don't know how much recursion theory I can use for you, but it's definable in the standard model by a sigma 1 sentence. Okay? And so because everything true in the standard model holds in T, then if you can prove A in T, then prov A is going to hold in the standard model, where prov is the arithmetic sigma 1 sentence which defines the theory in the standard model. And therefore, because everything in N is in T, well, you can prove in T prov A. So it's true because we're assuming that the theory is axiomatic, so it's provable it's definable in the standard model by a sigma 1 sentence, and anything you can do in the standard model you can do in T. That's the answer to your question.
I was thinking about the last consideration concerning the applications of. I really like your approach of very big number, and it won't mess the applications that there is. But what about the new applications that this kind of theory could provide?
Yeah.
Because I can see the proof of completeness is a good application, but there is something else, like to have numbers that are successive of themselves. It's quite strange. Right?
Okay, so this is a really interesting question. Okay. Normally, when we apply arithmetic, we apply a consistent arithmetic. And if what I said about the least inconsistent number is right, then, there's no funny business until you get to a very large number. So suppose n is smaller. So it's only, 10 to the 10 to the 10 or something like that. Then maybe this has physical significance. So maybe there are some physical phenomena such that the arithmetic we need is actually inconsistent arithmetic. Now, okay, I don't know of any physical theory currently like that. However, mathematics and physics are very strange things. And physicists, often, a branch of pure mathematics is developed which finds an application in physics only later. So when group theory was discovered or invented in the 19th century by people like Galois and Abel, it had no physical application. But then an application was found in special relativity. So we know that sometimes there are bits of pure mathematics which find an application later, depending on what physicists discover. Now, it seems to me entirely possible in some sense that 200 years' time, if the human race survives for 200 years, which is not assured by any means, okay? But if science is still going in 200 years, could the physicists discover that this was exactly the branch of mathematics they need to do what they want? Well, maybe it's possible. And if they did, the physicists would say that it's the correct mathematics to their application. So, physicists are much less conservative than logicians. Physicists will help themselves to any bit of mathematics which works, and then they'll tell you that tells you about the structure of reality. So, my reply to your question is that, well, look, I don't know of any possible application for inconsistent arithmetic now, but hey, who knows what's going to happen in 200 years' time? I won't be around to see it. I wish I could come back and find out.
Thanks for the presentation. I have a question about the logical status of the concept provable in your theory. It's possible, for instance, to consider provable as a model operator, for instance, in Bolos' model logic of probability. And my question is about the reason why provable here should be considered as a predicate and not as a model operator, because there are logical differences between both treatments. Think, for instance, about von Wright logic of truth. In his logic, for instance, truth is treated as a model operator as well. And the difference between both, as I think, correct me if I'm wrong, but for instance, it's possible to say that consider probability as a synonym of truth. For instance, you say it's true, a proposition is true, its negation is true, but it's possible to say that the conjunction of both these propositions and negation are not true in the system. And in this case, you avoid inconsistency by treating truth as a model operator. So my general question is, what about the philosophical reason or the semantic reason to treat probable as a semantic predicate and not as a function, a linear function?
Okay, good. So provability is a predicate almost by definition. So we're working in standard first-order logic, where you haven't got modal operators. Provability is a predicate, and that tradition goes all the way back to Gödel, of course. So, at least as far as that goes, I'm being very traditional. Okay. Now, of course, that doesn't mean that you can't have a modal logic where prov is effectively a modal operator. We know you can do that. Okay. So there are systems of modal logic where there's an operator prov, and it behaves very much like the predicate prov in, say, Peano arithmetic. And you get a kind of unusual modal logic. I think it's usually called G. It's investigated by people like Boulos. What makes it unusual is that the accessibility relation for the modal operator is kind of unusual. And you have logical truths, which are kind of unusual because you have this unusual constraint. So, I mean, what... no, that's correct, because what you're not going to get the analog of, you've got the analog of Loeb's theorem, okay? So you're not going to have, so take prov to be a modal operator, you're not going to have if prov A then A, because that will be Loeb's theorem, and you haven't got that, okay? Now, you can certainly do that. Now, interesting question. What happens if you do the same thing for the inconsistent arithmetics? Don't know, but you can certainly do it. What you're going to get is a modal logic. It's going to be a paraconsistent modal logic, but, we know these things. What paraconsistent modal logic are you going to get? Well, that's a really interesting question. I don't know the answer. What you are going to get is reflexivity, okay? Because you've got Loeb's principle back, but you're going to get some other stuff too. What you're going to get, what the theory is going to be in general, I don't know, but that's a really interesting question.